Hi, in this video we're going to look at the vector projection and how it continues on from the scalar projection we did in the last video. So to start with, let's talk about the scalar projection. So that's here. If we're given the vectors in magnitude and direction form, we can calculate it this way, where we're simply finding the adjacent side of this triangle using this formula down here. Now, if we're given in component form, like I have over here, so we've got our xy, x1, y1, what we do, because it's really easy to find the dot product of A and B when our A and B are in component form, we can use our definition for dot product, which is A dot B equals the projection of A on B times the magnitude of B. So we can use that formula. So it's the projection of A on B is that length, and we're multiplying it by this length, and that tells us our A dot B. That's fundamentally what it is. But we can take advantage of this formula and rearrange it. So if I divide both sides by the magnitude of B, I can work out what my projection of A on B is here. So we're doing it in a slightly different way, which is more convenient based on the information that we're given. So we're going to continue that today with vector projection. So vector projection, the difference is we're turning our scalar projection length into a vector. How we do that is we get our length and we multiply it by our unit vector. So effectively what we're doing is we're getting our unit vector here and we're scaling it by our scalar projection length, and that scales it up into our vector projection. So what that looks like in terms of our component form. So let's draw it over here. So we've got the exact same thing. This time we are determining our projection of A on B by doing A dot B on the magnitude of B. Okay, so that gives us our length. If we want to turn that into a vector, we need to multiply the B unit vector by our length. We need to scale it by that length so that the vector scales up. So all we're doing is we're getting our projection of A on B and we're multiplying it by our unit vector. So exactly the same as what we did here. If I'm multiplying it by my unit vector, it now becomes a vector. So both are exactly the same formula. In both we have the projection of A on B equals the scalar projection times the unit vector, exactly the same over here. Okay, it's just the way that we calculate the scalar projection is a little bit different in this case. So let's have a look at an example. Zoom out. Okay. So we've got two vectors here. We want to determine the projection, vector projection of A on B. So visually what that looks like. Again, our visual's super important so we can know what we're doing. We're trying to find that vector there. I know I can find my scalar projection by finding my dot product of A and B, which is going to be this giant length out here, and then dividing by this length, and that will give me my scalar projection here. So B. So let's just do that first. So A dot B is 26 on 10 plus 12 on root 29. Okay, so that's my length, my scalar projection of A on B. When I'm calculating the vector projection, I'm getting my scalar projection and I'm timesing it by my unit vector. So let's calculate the unit vector. We'll do that up here. We've got 5 squared plus 2 squared. We've already done that, haven't we? It's root 29. So the unit vector is 1 on root 29 times by 5/2. Now, when you're doing this, it's very convenient not to rationalize this, because notice when I multiply this by that, the root 29s are going to times together to become rational. So over here, what that equals is scalar projection of A on B by my unit vector equals and I would just leave it in that form, but you can scalar multiply. You can multiply the fraction in if you like. So notice here, now that I've written it out, there was no point to rationalize it in this form if we're going further to work out the vector projection, because it ends up rationalizing itself when we multiply by this. So what has happened is that because we have the magnitude of B on the bottom of this, and when we're calculating this guy over here, we have the magnitude of B on the bottom, we get 2 square roots undo themselves to become a whole number, so we're good. So vector projection, all we're doing like we did previously is we're getting the scalar projection and we're multiplying by the B unit vector. So that's the video on vector projections. I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.